Okay, so hello again. I would like to introduce Julian Bangert and Mr. Sergey Bratus, and they will talk about ELF eccentricities. Okay, so let's start. The floor is yours.
Thank you. Thank you for having us here. We're from Dartmouth College, which is a small private college in the northeast of the US. With the weather, that's just about the same as here. So what we're going to talk about is the L part in the ELF, executable and linkable format. Now, this format is, of course, ubiquitous on Linux and on many other Unisys, and people mostly pay attention to the E and an F. Well, the E is for executable, the F you have to parse, and sometimes it's that sort of a task, indeed. But the linking is not particularly well understood. That is to say, it sort of works by magic, and people pay no attention. But in fact, if you look at the data structures that go into linking, they're quite complex. If you look at the data structures that go into loading, they're quite complex as well. And so you have both the kernel and the dynamic linker loader interpreting those and mapping kernel memory, creating new VMA structs, creating interesting memory trees. So when you're controlling that, you are actually looking at non-trivial change of state in the kernel itself, let alone in your user memory. And so this is done by the exec system call. This is done on behalf of your process by the dynamic linker. This is done by any analysis tools, such as IDA Pro. And in every case, the interpretation turns out to be slightly different. So it's important, and Julian is going to take through the effects of those subtle differences. And we're going to show why they matter. So we want to essentially strip the mystery off of that format and encourage you to play with it. And of course, ELF has cousins. PE is a very famous cousin. If you have not seen the Corkamy PE 101, download it and peruse it. PE is quite interesting in its own right. And it has another cousin, which lives on much shinier boxes. And we're intentionally leaving this space blank, even though it's a rich target. And so the two angles which we're going to look from at the L in the ELF are what we call LANGSEC, language-theoretic security. And the first angle is that any input is really just a program. So if you think of the input being input, sucked in by your input handling code, then you should imagine that this input actually serves as a program. It's as if your input handler is the processor that fetches those input bytes and goes through some state changes and transitions. This way, you can actually understand in clear theoretical terms what an exploit is. An exploit is a program running on that virtual processor that is your code that handles inputs. And bugs may or may not be involved, in fact. Bugs may create a more powerful instruction that will make the input handler from an innocent finite state machine into a full Turing machine, the most powerful execution model. Or, in fact, your format may be rich enough to do it on its own without any bugs involved. But ultimately, if you are to trust your machine, if you are to trust your execution, you need to understand exactly how your input runs on your input processor. So only a well-defined execution model of input on your code can be trusted. Otherwise, you're just pwned. And one way to go about it, the way to go about constructing input-safe software, is to treat the input handler as a recognizer automaton, be it a regexp a finite state automaton, be it a push-down automaton, a stack machine, be it something slightly more complicated, but you're basically expected to express what your input is, what your data that you're reading is, as a language recognized by such an automaton, and then implement that automaton. That way, you will understand exactly how input runs on your code, and so you will be safe from unpleasant surprises, shall we say, or being pwned. And the other angle is what LANGSEC movement started from. Meredith Patterson, a co-inventor, will be closing this conference, and I urge you to attend her talk. So she and her late husband, Len Sassaman, noticed that a special class of subtle vulnerabilities existed due to two parsers interpreting the same data slightly differently, and they call it parser differentials. And this is really a recipe for disaster. When you have one input and two parsers, it's a tale of ponage. So in their case, they noticed the differences between the parsing of X509 certificates by the certifying authority, which was happy to sign, and the browser that saw the signed certificate differently, and saw a signed name for eBay or Amazon when the certifying authority thought it was signing some insignificant site under some sort of a private ownage. So ELF and its cousins have a lot of redundant data. And so from this angle, you just wonder, when the data is redundant, which version will be trusted? And we counted the ELF parsers in the binary toolchain. There are at least two. There is one in the kernel and one in userland. So if the data is redundant and inconsistent, which one will be trusted? And we're going to show an inconsistency between the kernel's bin format, the ELF format parser in the kernel, and the LD.SO. And with that, we're going to basically take the two of these angled views and see what they show on ELF. And I'm turning this over to Julian, who actually did all the work.
Well, thank you. And take the microphone. Okay, so hello. I'll be giving a brief overview of the ELF file format, but to differentiate myself from an incomplete header file with really bad puns inserted on the side, I'll try to also show many of these vulnerabilities that Sergey just mentioned, where one parser treats the ELF file just a slight bit differently than another parser, and therefore you get different security assumptions being made and being violated. So on most Unixes, ELF is used for a variety of things. It's used both for storing executables and shared object files, but also for all of the intermediate object files that come in your compilation toolchain, in addition to core dumps and other things like kernel files. The ELF file format, and this is important to keep in the back of your mind as you're listening to this, was created to replace an older file format called simply AOUT. AOUT was not a single file format, but just whatever nasty hacks the Unix kernel developers needed to make something run. So AOUT has continuously evolved since the first Unix kernel ever for the PDP-11, and every time they added a new feature, say virtual memory or shared libraries or the ability to take core dumps, they basically had to rewrite the entire AOUT format from scratch. Initially, that wasn't so bad because only the kernel and the compiler touched it. But then people started making more and more tools like debuggers. And then every time someone added a new feature to the kernel, you basically had to rewrite all of your tools, which gets nasty very, very quickly. So the wonderful people at a small Unix developer, or at the time a rather large Unix vendor known as the Santa Cruz operation, which at some point turned from an actual software development company into a lawyer think tank, assembled all of the other Unix vendors at the time and tried to come up with a uniform standard for handling everything in any way related to executing code. And they came up, after many, many hours of committee sitting, with this standard known as the Executable and Linkable Format, or ELF. Its original intent was to not only store code and data, but also store the metadata about it, so that you could understand the data in a more abstract format, and your old tools can understand new changes that might come about in the executable format. And it also allows you to compose different code so that you have uniform mechanisms for, so the difference between assembling object files into a shared library and assembling the same object files into an executable file is no longer any, you don't need any different tools for that anymore. And this extensibility also allowed the Unix developers to define new mutations on code, such as ASLR and the relocation process for shared libraries. And the initial vision, as I already mentioned, was that they suddenly no longer need different parsers or different input-output stages for all their different tools. In the old A-out days, the debugger could share absolutely no code with the linker at all. Their idea, however, was we're going to have a uniform file format for that. And so we just need to write one single ELF parsing library, and that we can reuse in all of our code. Similarly, when you're writing a debugger, you no longer need to write a debugger for all of the 20 Unixes that are out there in the market, but you can just use one tool, and they all use the same file format, so it'll all be compatible. And this was just before they had finished, just before they started developing ELF. They just finished developing TCP/IP, where they had this cool idea known as Postel's principle. Ignore any input you don't understand, or be liberal in what you accept, but be conservative in what you produce. As in, accept all of the input that somewhat resembles what you know, and output only the things that you actually understand. They took the first half of this very much to heart, and they accepted as input just about everything. However, they kind of forgot about the second half, and also produced just about every output you want it to be. And especially when you're dealing with something as sensitive as executable files, it's of course a great idea to modify data that you don't really understand. But as critical as I may sound of this is what allowed things like shared object and ASLR to be implemented on Linux in the real world without having to start the entire Unix evolution from scratch. In reality, this nice flexibility was not quite implemented that well. As opposed to having just one uniform parser library that everyone from the kernel to the dynamic loader to the compiler writers would use, everyone figured that you don't need the whole complexity of the ELF format. After all, they're only interested in part of the data. So wouldn't it be nifty if we could shave a bit of our code base off and just write our own parsers? So by now, and also the other thing is that when people were building parser libraries, they often built them together with the very same tools, to the extent that the standard GNU ELF parsing library, which is libbfd, is not actually released as a separate dynamic library, because every single GNU utility that uses them maintains their own private fork of it, and then people just push around patch files between them, or they don't. And with the original vision that went into it of having a clean file design that allows you to easily create extensions to the executable and linkable format, they had a few rather vile design patterns creep up of them in the back that we choose to present as horror movie titles. We have the Revenge of the Committee, because they designed their file format to take all of the odd eccentricities that were present in the dozens of now completely obsolete Unix kernels. And they also, at the same time, this was when machines were a lot slower. So they added a lot of really, really nasty performance hacks that are now coming back and are still part of to bite us in the ass. The central pattern that we're going to see that makes most of the vulns that makes most of the bugs that we have in there is that we have two different parsers that treat the same file structure in a very ad hoc way and trust that if there are two representations of the same piece of information, well, of course they're going to be consistent, because who would write inconsistent information to a file and then send it to a higher privileged parser? So you might have this one executable file. If the Linux kernel looks at it, you get one description of the executable file. If a different parser looks at the very same file, maybe just in the very next function or in the very next stage of the process initialization, it will see something completely else, but it assumed that the Linux kernel previously also saw the same representation. And And with that in mind, I'm going to start my overview of the various data structures present in an ELF file format. I'm going to try to point out where such parsing ambiguities can arise. At the very beginning of an ELF file format, that is at file offset 0, there's the ELF header. This contains a few magic bits to identify that, yes, this is really an ELF file, and this is the correct version. We haven't changed the standard again behind your back. The Linux kernel actually checks for that at the beginning to know that you're executing an actual ELF file and not a shell script or something like that. It also contains information about what particular kernel this file is supposed to target and what particular CPU, etc. And more importantly, it contains two offsets to two tables that will describe the rest of the file. One of them is the program header table. The other one is the section header table. First, we'll look at the section headers, which are the more detailed of the two tables. The section header table is nothing but a table that attaches a label to a given range of bytes in a file. It says, well, everything from byte 100 to 2 megabytes is going to be our text segment, for example. In addition to that, it specifies what type of data it is. For example, if it was a text segment that contains your program's code, it would say this is a part of the program. If it was a symbol table, it would say, hey, this is a symbol table here. Again, SCO wanted the ELF format to be as extensible as possible. So future tools might not know about the new kinds of data you would want to store in an ELF format. So in addition to telling you what type of data this is, they also added a special flags section, which tells all of the tools interacting with an ELF file how to interact with this particular section. That's where you say if it contains executable code, if this is supposed to be readable or writable at runtime in the virtual memory space, or if this is just some metadata that will not wind up in the address space, and also if any special parsing hacks need to be used in this particular section. And usually when these flags are set, you know that something funny is going on. The other thing that it specifies for that range of bytes in the file is where this range of bytes is supposed to wind up in memory. So it contains a virtual address, and for compatibility with some embedded devices, also a physical address where you're supposed to map this particular area of memory. The issue, we're already running into the first issue here, is that it is just a flat table of saying, please map this range of bytes to the following virtual address. There is absolutely no guarantee within the file format that says that these ranges are not overlapping. So if you're trying to look at a binary file and you're saying, oh, well, what do these particular bytes mean? You can't just walk the section header table and look at and then see, oh, well, this is going to be a symbol descriptor, or this is an assembly instruction. But instead, it might be that you have the same byte in the file meaning different things. It can be part of a relocation table or part of a symbol table. And frequently, this can confuse tools unless they're very careful about parsing, because the format is so context-dependent. The much bigger issue with the section table, however, at least at the time, was its size. Back when this was designed, you had around 30 entries in a typical section header table. If you just wanted to map this to memory straightforward, you would have to have 30 memory map calls. Again, this was on the original SEO Unix System 5 kernel, which barely survived 30 memory map calls in the first place, and if you wanted them to be done before the user had switched back to his old VAX with VMS, the chances of success were lower than a Russian roulette with an AK-74 or 47. And so they decided to go for the good old-fashioned performance hack and add a second table that describes what to actually do at runtime, as opposed to the section header table, which is only used by fancy tools like a debugger that can run slower. This program header table usually has many less entries, or has much fewer entries, but basically contains the same information. It says, please map this range of bytes in a file into the following range of virtual addresses. Well, there is absolutely no guarantee, again, and no one really bothers about checking if these two tables align at all. So for example, you might find out a flash drive somewhere, and that's labeled Hello World Program Professional Enterprise Edition. And because you've always wanted to have a program that prints Hello World to your screen, you decide to run it. Because at one point, your information security people told you to not run binaries off a USB disk. You go in and look at it in IDA Pro, just to check out what is going on there. And you disassemble it in IDA Pro, and you see, oh, well, this program does nothing but print Hello World to the screen. So you go ahead and run it, and then you realize that you must be in some very, very weird world, because apparently its output has been mirrored. After you check that you're not drunk, but that, in fact, this is what was printed to the screen, you realize that you've been had by probably one of the oldest tricks that can be used to obfuscate an ELF file. Because IDA Pro and other disassemblers mostly follow the section table, because after all, the section table is more granular, so you can get more information from it. It can happily give you one view of the world, where in fact this program is printing hello world. However, when you're trying to run this particular program, the kernel follows the program header table, which can set up a completely different address space, giving you a completely separate program to run. This, however, is not nearly the worst parsing ambiguity. A much bigger issue stems from the fact that there are, again, two separate ways you can parse an ELF file. One of them is when you have it as an actual file somewhere in your file system. The other is when the ELF file has already been at least partially loaded, and you're currently within the virtual memory address space. In a normal sane binary produced by the friendly compiler, this is a pretty straightforward mapping. So if you have some piece of code that you can use to parse an ELF file with the read system call, that you're just reading byte by byte from a file system, and you want to write some code that looks at the virtual address space, because normally the mapping is relatively linear, you can basically reuse most of the same code. And of course, that's what people do. However, the issue is that the very same file you're trying to parse also describes how to set up that address space. So if you have some knotted, weird construction that instead of having a nice linear mapping tries to set up something rather convoluted, most of the tools that parse ELF as it is mapped in memory, for example, the dynamic loader, tend to blow up. To understand this, you need to look into the program header table in a bit more detail. In addition, because while the actual meaning according to the spec is take this range of bytes and please map it to this address range, the way it is actually parsed by the tools is that it iterates through the program header table, looks for PT load headers, and translates each of these to a memmap system call. As the evasion team, which developed an iOS jailbreak, noticed, the memmap system call, according to another committee, which may have shared a few members with the ELF design committee, the memmap system call, when you're specifying an address to it, and that's what they're doing, because with a normal memory map system call, the kernel can basically place the mapping anywhere you want, but if you have an executable, you might want code to wind up at a certain relation to data, so that you have some level of sanity. The semantics of the memmap system call specify that the kernel should replace any previous mappings at that particular address. If you have program headers that tend to overlap, the one that actually counts in setting up the address space in the end is the last one that has been mapped. Much nastier tricks could be had if, for example, you were to also map some program header over the dynamic linker's internal control structures, and if Bex, who is sitting in the audience back there, has done fun things by feeding other ELF structures into themselves in creative ways. So the short version of this is that the order of these PT load program headers is actually important, but is mentioned nowhere in the spec. And because most tools are coded according to the spec and then validated against sane object files, most tools tend to ignore that fact, which tended to completely kill the Apple iOS code signing, which is using a close cousin of ELF, Mach-O. And the first rule of Mach-O is that you don't talk about Mach-O. In order to show this problem with the parsing ambiguity, you have to look at how an ELF file, at the life cycle of an ELF file. If you're trying to execute a binary, say your normal bin.ls, the kernel looks for the file, checks it is in fact an ELF file, and then reads the program header table into the buffer. It does that by looking at the ELF header and seeing, oh, well, the program header table is living at offset 64 within that file. So just read that particular offset until and the ELF header also says how many program header tables there are. It then checks for a special program header called PT-interp, which tells you where the dynamic loader is supposed to be. So the kernel, fortunately, was lucky enough, or the kernel developers were intelligent enough to understand that parsing this entire complicated file in the kernel would just lead to an endless succession of fail. So they moved the actual parsing of most of ELF into a special user space binary called the dynamic loader, which actually runs before the main code if your program ever executes. And they then load this from a shared object file, usually lib LD.SO, and then transfer execution to it. However, because the only place where they specify where the program header table is, which the dynamic loader needs to parse and analyze, they have to tell the dynamic loader where that table is wound up in memory after they processed all of the load system calls. They do this by virtue of a special structure called the aux vector, which is also used to parse things like command line arguments and environment variables. So with a normal binary, this would look something like this. You start off with the file view, with the file on disk, with the ELF header at the beginning, followed by program headers. Then you have some other read-only data that is not supposed to be changed during the execution of the program, say your actual code or some constants, followed by read and write data like your data and your global variables and your heap. The kernel then reads all of the ptload entries in the program header table and maps various parts of the file first into the virtual address space. The kernel then looks at where did the program headers start and sends this offset down to the user space, where the dynamic loader will follow this link and then pass all of the other entries in the program header table. If you actually look at the source code of this, you will notice that the calculation that they do is relatively straightforward, to go from file offsets to virtual address. And what they do is they go through all of the ptload entries to set up the virtual address space and set up all of the internal magical kernel structures that make virtual memory work. The first one of these, the lowest virtual address, or the difference between the virtual address and the offset, is actually recorded, and thereafter never added. They then just assume that because with most binaries, this mapping is perfectly linear, adding the offset within the file to the lowest virtual address will result in the virtual address of that particular data structure in the virtual address space. However, because there are absolutely no restrictions on how we set up this virtual address space, and also no restrictions on how we set up the file space, we can make sure that this assumption completely fails. Again, this doesn't happen in any binaries produced by a compiler. So far, most people, this is rarely noticed, and there's no particular reason why they should have fixed this. And this is one of the issues that you get if you're following the actual examples produced by the output, as opposed to having some rigorous spec. But you can't really lay the blame at the kernel developers, because the spec is so ambiguous that there is basically no correct way to parse it. So if you craft the file to look slightly different, where you put the program header table at the end of the file as opposed to at the beginning, the kernel will still find two separate mappings. However, the program header table will no longer be mapped as part of the first mapped segment. So adding that particular offset to the beginning of the first segment will just point somewhere random in the address space. Because we know we can control this address space, we can make sure to map that this is actually some other structure that we've mapped. And so some random bytes in your .data section will be interpreted as a program header table. And the dynamic linker will happily trust all of the data in there and walk it and perform computations based on it. So what do we do if we control this program header table without any of the other tools knowing about it? Because the issue here is that all of the other tools which will look at the file will find the original program header table that is unmodified. And so we should see what we can do if we can use this parsing ambiguity and sneak some program headers past IDA-Pro. We can't actually change the layout of the address space, because at this point, the address space has already been set up by the kernel. However, there's a much more interesting entry called the PT dynamic program header, which gives the virtual address of the so-called dynamic table. Again, the main objective in adding this program header hack in the first place was that SCO wanted to make the linking really fast. So that not only does the kernel not have to read the section header table, but they also wanted to make sure that the dynamic loader itself also doesn't have to follow this table. So they added another special section called .dynamic, which contains the addresses of most interesting objects in the virtual address space after it has finished loading. As opposed to the section header table, which talks in terms of file offsets, this here talks about virtual addresses, which again we can control and point to weird things. There are many ways to find the dynamic structure. One of them is using the PT dynamic program header, which is the way that the dynamic loader itself does it. And after that, you can either follow the virtual address that they provide and translate that virtual address to the tables you've just created, or you can just trust that whoever put this program header table in there hasn't messed with it and has conveniently put the right offset into a field. A lot of tools tend to follow that. If you manipulate the offset to point to something else, they'll just happily think that whatever is at that offset is also the valid dynamic table that is actually being used. Alternative ways of finding it, especially at runtime, tend to also be to resolve a particular symbol or to just look for the .dynamic section. Within the .dynamic section, we have a few entries to describe the location of For example, the symbol table and the relocation table. And also a list of all the shared libraries needed to do this. These three tables are necessary to implement dynamic linking, which leads to a few other entertaining things. One of them is that shared libraries and position-independent executables, for example, used with ASLR, are loaded at a random base address. So the dynamic loader, when initializing the process and looking for all the dynamic libraries that you want to have loaded, tries to allocate space for the entire library. It needs to find somewhere where it can possibly map that. So first, and it does this by asking the kernel to deal with the entire address space layout by just memory mapping a chunk of memory that size. So it needs to figure out the size of the shared library. Normal compilers emit all of their segments, that is the ptload program header entries, in sorted order. So you can figure out the size by just taking the beginning of the first one and the end of the last one and subtracting them. If someone really, really nasty would have, by accident, maybe moved these things out of sorted order, the dynamic loader certainly never checks. It would still happily continue allocating a chunk that might be allocating a chunk of virtual memory that would be much too small to actually fit that shared library. Now, initially, when I saw this, I thought this would allow me to control arbitrary memory by virtue of then the dynamic loader going in and remapping. With modern versions of GNU-libc, this is no longer so, because they actually only call memmap once as a performance optimization. However, they still call memprotect. So you can call memprotect in arbitrary ranges of your binary, if you control the so for example, you can defeat protections like the non-executable stack. And if you want to create a shared object in a popular library somewhere, you can easily hide a program header entry in there that will make sure that none of the binaries linking against this shared object will ever have a read-only stack or a non-executable stack or any of these protections. Yet all of the tools that will scan all of your binaries will not notice this sneaky way of disabling that protection. The other interesting thing in there is that because the ptloads are designed to control virtual memory, they almost immediately go down to the kernel's virtual memory structures. So you can arbitrarily control your process's virtual address space with these program header tables. The interesting thing there is that the granularity of the MMU on most processors is 4 kilobytes or 16 kilobytes or something like that. However, the ptloads actually allow you to specify an arbitrary precision in there, which is impossible to implement because you can't have a virtual memory system with arbitrary precision on existing hardware. So somewhere along the way, the addresses within a ptload have to be rounded up or down to correct page size boundaries. Again, most tools tend to know about this in advance, so they actually set up their ptloads to not require any of this rounding. But a lot of interesting things happen that, for example, again, disassemblers tend to handle the rounding a lot differently than the kernel, because this is not assumed to be an implicit thing, but the actual adjustment of memory addresses happens spread out throughout a very large code base. And the other inherent feature of ELF is that it combines different binaries, so you can spread out whatever massaging you want to do to the address space between different shared libraries and get lots of interesting effects there. By virtue of remapping things, for example, from a shared library that your process depends on, you can also remap the linker's internal data structures to point to something else. So together with that hiding trick that we have for hiding the dynamic table, which controls where all of these structures are read from in the first place, we can arbitrarily hide GOT entries, dynamic symbols, or relocation entries, which is what the kernel actually uses to make shared libraries, or the dynamic loader uses to make shared libraries work. Symbols are a much more fine-grained definition of what happens in what segment, and at what virtual address to find a given function, for example. And these are used by the dynamic loader together with relocations to make sure that when you load a shared library into your address space, the existing code in your text segment knows where to jump to. To implement this very particular small use case, they give you an engine that performs some computation on the symbol values and writes the results of that computation into memory. However, the symbol table is also just another piece of memory loaded in the virtual address space. So if you make that particular computation engine write its output into its input, you in fact get a Turing machine, again, as Bex has demonstrated and will remind us of in tomorrow's talk at noon, which you should come and check out. More in general, a lot of this research has been part of a project we have underway to formalize what the actual computation of linking is. But until we come out with a result of that, and for the purposes of this talk, we'll just assume that roughly linking is just combining data from different ELF sections, resolving the symbols, and then applying those relocations, which is a relatively straightforward computation conceptually. However, again, various committees in the 1980s, when your processors were slow, had designed that this had to be really, really fast. So as opposed to walking down a symbol table, which contains strings that have the name of every symbol, and then finding out, well, it wasn't in the first shared library, so it better be in the second shared library, and walking down that chain, performing lots of string comparisons along the way, they tried to speed it up by adding a hash table. The point of a hash table is to get you from a symbol name to a particular index within a symbol table. And it is relatively straightforwardly implemented. You first have a hash function, which produces an output somewhere between 0 and n buckets. And so you have n buckets entries up here, which contain indexes into the symbol table. The dynamic loader, when it tries to find a symbol, then looks at that particular symbol's name. If that should by any chance not match, it will look if there may have been a hash collision earlier, because n buckets is typically something small like 63 or 67. And for each symbol, there is a next link in this chain block, which forms a simply linked list of hash collisions. And it just walks this list until it hits the end. The particular code for that is, again, relatively straightforward and assumes that this hash table was generated by the actual GCC compiler or linker. If, however, someone, again, were quite evil and were to make this linked list a circular list, for example, having one entry point back to itself, neither of these checks would ever succeed. And the loader would just be stuck looping on that table. A lot of effort has been spent by some programmers in making sure the applications can't be debugged. And reverse engineers have spent a lot of effort on finding clever ways to, for example, inject the debugger into the same process that you're in. This is another technique that you can use somewhere along those lines. So, for example, if you're trying to debug Skype or some other damn application that really doesn't want to be debugged, you might want to set a breakpoint on the first time they call a certain library function. So you might want to set a breakpoint on malloc. If you do this with a normal ptrace interface, they'll most certainly detect that. However, if you can modify your libc so that the hash table entry for malloc contains a loop, the first time they'll call malloc, the dynamic loader will walk this table and then get stuck on that particular entry. And you can then go in and attach your FireWire dongle and dump physical memory, or maybe cause the process to dump core and look at the core dump. The other advantage is that because at this time it'll only ever be accessing that very region of memory, you can also arbitrarily modify it. And once you're done with your debugging and inspecting it, you can go in and restore the original hash table link that was in there, and the dynamic loader will sail right through. In order to look at these ambiguities, and also in particular to get rid of some of them and detect them, we developed a toolkit called Mithril. Sergey happens to be a big Lord of the Ring fan, and Mithril is this mythical element which the dwarves use to forge the best swords. Elves, sorry. It's Mithril, okay. Indeed. So we've designed the previous state-of-the-art of ELF manipulation toolkits is ERESI. ERESI did not send out to be an ELF binary toolkit, but ERESI tried to be one of these awesome tools that allow you to debug absolutely anything that doesn't want to be debugged. And as part of that, it has this nice little feature that allows you to insert a debugger into an ELF binary. As part of that, they had to write a very comprehensive ELF manipulation toolkit. However, ERESI is somewhat old and suffers from a few issues, and they've only restarted development about 6 months ago. And so even though Bex and I have based a lot of our research on his tools, when and big fans of some of his outcomes, it isn't terribly great to actually work with this tool. Or in my opinion, the biggest issue that ERESI has is that it tries its in-memory representation of an ELF file is almost exactly the ELF file as it would wind up on disk. Because ELF is so context-dependent and information is stored in many different places, it's incredibly hard to keep a consistent in-memory representation as you're manipulating things. The other thing is that it was written by a rather large team, so every single function, for example, the function to inject symbols, touches almost every bit of the ELF file. So to try to make space for that particular symbol in the table, then move everything else around, and then update all of the metadata. The next injection function, for example, the one to inject another function of code, has to perform almost exactly the same manipulations, but it does them just slightly differently, which again is a very bad thing, not only from a security standpoint, so you could probably trick ERESI into doing bad things, but also in terms of just not producing correct output most of the time. So Mithril tries to keep an in-memory representation that is much less context-dependent and completely independent of what is actually winds up on the disk. Parses the ELF file and all of its ambiguities into this cleaner representation, and then writes it out again. So if you load a certain ELF file and then save it back immediately, you get something completely differently. But semantically, the two executable files will be equivalent. Currently, we have this as a Ruby prototype and do a lot of our things with that, but eventually we hope to re-implement it in C, in particular with Meredith Patterson's Hammer library. Again, she'll be giving the closing keynote, which I encourage everyone in here to attend. And the parser component, that is the component that analyzes existing ELF files and tries to get rid of most of the ambiguities, is relatively stable, and I've not found a binary that blows it up yet. However, the generating part, that is writing out an ELF file corresponding to our cleaner representation, is still a bit of a prototype and has some issues, for example, with creating shared libraries. And this development in that is actively underway. In particular, also, with demonstrating some more of these vulnerabilities by allowing you to have just slightly wrong ELF files. And the source code for that is available on GitHub. The link will be on the final slide. Again, as I mentioned with ERESI, if you wanted to manipulate an ELF file, either you or the library author who wrote that particular injection function had to take care of shifting around all the other bits in the binary and keeping track of all the dependencies manually. Whereas with Mithril, inserting a new piece of code, for example, is relatively straightforward. You just define a Ruby class for it. That is so that the generative model afterwards, you can have some clever callbacks in there to adjust whatever data you're injecting based on the file's layout, and you just push it on top of a Ruby array. Similarly, you can inject symbols and relocation entries by virtue of just appending them to a Ruby array. And once you're done with all of that, you tell Mithril to write it back to a file, and our library takes care of all the layout work and making sure all of the bits fit in. And it will warn you if you've tried to do something inconsistent like overlapping virtual addresses, unless you pass in the special --back switch, which will disable all of the sanity checks. As part of this research, we'd like to thank, in particular, the LANGSEC conspiracy with Sergey Bratus and Meredith Patterson and Lance Sassaman, who have inspired us and shown us that these parsing vulnerabilities can actually cause severe security issues. Specifically with regard to executable files, there is the awesome Corkami project, which is a very nice manual of some of the oddities found in the PE executable format, which is even worse, like everything at Microsoft designs. The ERESI project team, both past and present. And specifically with regards to ELF, there is a cool website called TinyELF, where they show you that by how you can minimize the size of an executable file down to something like 60 or 70 bytes by cleverly overlapping these various structures, which gave me this original idea. And of course, I have to both thank and blame the Grug and Silvio Cesare for getting my advisor Sergey hooked on ELF, and similarly, many of the interesting FRAC articles written about the executable format. In this case, we're done way ahead of schedule, so if anyone has any questions or comments or would like to throw rotten tomatoes, please go ahead.
Okay, so if not, thank you very much for your speech.
Thanks.